Hello again, mathematicians. In this video, we're going to review how to simplify radicals. Before we start simplifying, I want to review radical structure. Another word for radicals is roots, not just square roots, but all kinds of roots. What I have here is the general structure of a radical expression. Whatever is under the radical, whether it's numbers or variables, is called the radicand. This symbol here is called the radical. And the number that's attached to the radical is called the index. And the index tells you what root you're taking. So are you taking a square root, cube root, fourth root, fifth root, 20th root, whatever it may be. Okay, let's try problem number 1. It's asking to take the square root of 63x to the third. Now I know I said before that radicals have an index. This is really your standard root though, the square root. You could write a 2 there, but that's not standard notation. People just assume it's a square root if there's no index. We may not know how to take the square root of 63 or x cubed, but we should know how to take the square root of something like 9. So square root asks, what can you multiply by itself? And you're multiplying it 2 times to give you 9. And the answer to this would be 3. We should know that. So my advice is to tackle a problem that you don't know by looking for something that you do know. So can I factor 63 and find perfect squares within 63? Can I do the same thing for x cubed? So if I factor 63, I know that it's 7 times 9. Now I know with factor trees you could factor this 9 further, but I'm not going to because 9 is a perfect square. And that may help me in a second. I can rewrite this radical then as 7 times 9 times x cubed, which we'll take care of in a second. When you're simplifying radicals, we can use something called the product rule and eventually the quotient rule. So the product rule says that if you have 2 radicals with the same index, you can rewrite them under one radical as a product under the radical. Now this is helpful because we can do the same thing backwards. So instead of writing it as one big radical as a product, we can split them into 2 smaller radicals with the same index. So I can really split this into the square root of 7 and the square root of 9. We'll go back to this x cubed. This is helpful to me because I can take the square root of 9 now. The square root of 9 is just 3. We can't take anything out of 7 because that's prime, so our 7 will just be our leftover. Okay, now I know that x to the third was there, so I'm going to put that back in now that I've taken care of the numbers. I'm going to take care of the variables. So the helpful thing is to try to break down x to the third into factors. Now I could factor this to be x times x times x, but none of those are perfect squares. So I'm going to be a little bit more strategic and break down x to the third in perfect squares. So x squared is a perfect square, and then what's left over would be 1 more x. So you have 2 x's here, 1 x here, that gives you 3 x's. Or by exponent rules, this has a 2, this has a 1, you could add them. So again, using the product rule, I can break this down into 3, because I've already taken that out, root 7, because I couldn't take that out, and then this is x squared times x, which I can then break down into 3 root 7 times x squared times the square root of x. Now this square root of x I can't simplify, but I can simplify the square root of x squared, which is just x. So what I have left here is 3 root 7 and x root x. Now this isn't proper notation. General rule of thumb, whatever has been simplified goes on the outside, so the 3 and x have been simplified, and whatever's left over stays under one radical. So that would be my final answer. So again, advice for simplifying radicals is if you can break it down into perfect squares for square roots, into something you know, it'll be easier to simplify. I'm going to let you try anything with a star on your own. Let's look at number 3. Number 3 of the cube root now, that 3 is the index, it's cube, of negative 8. So the 3 tells you you want to find something that when you multiply it 3 times, it'll give you negative 8. You may have heard before that you can't take the square root of a negative number, which is true because a square root asks you what can you multiply 2 times to give you that radicand. And is there anything you can multiply by itself 2 times to give you negative? No, that won't work, so you can't take the square root of a negative number, at least with real numbers. But can I take a cube root of a negative number? The answer to this question is yes, because you can multiply a negative 3 times and it will give you a negative. Negative times a negative is a positive, and multiply it by 1 more negative and you'll get a negative. So let's go ahead and try this. I'm going to break 8 down into factors until I find something that multiplies 3 times. So 8 is 4 times 2. You can break down that 4 into 2 and 2. So I can factor the cube root of negative 8 into negative 2 times negative 2 times negative 2. And just for another way to look at this, I can write this as the cube root of negative 2 cubed, because you're multiplying negative 2 3 times. And a cube root and a cube undo each other. They're inverse operations. So what you're just left as your answer is negative 2. So another strategy is if you can break down into factors and rewrite it as, if it's cube root, write it as a cube so they cancel each other out. It'll help you simplify. In this problem, there's nothing left over because negative 8 is a perfect cube. Again, try the star problems on your own. Let's look at a more complex one. This one's more complex because it has fractions and multiple variables. For this problem, I want to look at the quotient rule. The quotient rule says that if you have a root of something that's being divided, you can break it down into separate roots and divide those separate roots. So if I have like the square root of 1/3, it's really taking the square root of 1, dividing it by the square root of 3. And that's what I want to use on this problem. So instead of writing it as one big cube root, I can really break it down into the cube root of 125x to the 6th divided by the cube root of y to the 16th. The reason it's okay to do this is because these are equivalent expressions. So in this side, on the left side, you're taking the cube root of both pieces at once. You're still taking the cube root of both pieces on the right side. You're just doing the cube root of the top and bottom separately. So they mean the same thing. The reason I like to separate it like this is because you can kind of consider this as two separate problems and make it a little bit less difficult to look at. So I can basically ignore the bottom for a second and just solve this problem, which is something we should know how to solve. And when I'm done, I can solve the bottom problem, or the denominator's problem, and then rewrite them as a fraction at the end. So I'm going to pretend like this wasn't here and ask myself how I would solve this problem. What I want you to do is pause the video and complete this step based on what we talked about in the previous problems, and then I'll come back with the answer when you're done, and you can unpause it. So no cheating. Use this as a self-assessment of whether you can do this or not, and then check your answer with me. Go. Okay, hope you tried that on your own. If you did it correctly, you should have got 5x squared. So I factored 125 is 5 times 5 times 5, so I wrote that as 5 cubed. X to the 6, you can multiply x squared 3 times to give you that, so I wrote that as x squared cubed. Then the cube root cancels out the cubes, and you're just left with 5x squared. If you have any questions about that, please come to class with them. Now let's do the denominator, and then we'll rewrite it at the end. So I rewrote the denominator is the cube root of y to the 16th. So again, I want to try and factor that into things I can multiply 3 times, give me y to the 16th. Try that one on your own, and I'll come back again with the answer. Okay, y to the 16th is interesting because unlike 125 and x to the 6, it's not a perfect cube, but you can break it down into perfect cubes. So the thing you can multiply 3 times to give you y to the 16th would be y to the 5th. Y to the 5th to the 3rd would give you y to the 15th. So that means there's one y left over. So I can pull out a y to the 5th, and then there's 1 left under the radical. If that's confusing for you, you can factor this all the way. So really y to the 16th is 16 y's. 1, 2, 3, 4, 5, 6, 7, 8, 9. I know this is tedious, but I'm going to write it out to prove a point. I lost track now. No, I didn't. 3 more. Okay, so you're looking for groups of 3 you can pull out. And how many groups of 3 are there in y to the 16th? Here's one group of 3, because that's really y cubed. There's another y cubed. There's another y cubed. There's another y cubed. So that's actually 5 y cubes you can take the cube root of. So you can rewrite that as the cube root of y cubed 5 times. Y cubed, 1, 2, 3, 4, one more, and then there's 1 left over. So how many y's would come out? Well, the cube root of y cubed would be 1y. Cube root of y cubed again would be 1. And then you did it 5 times, you'd have 5 y's on the outside, and there'd be 1 left over. Now, I know that's really tedious, but it's another way to look at it. I will probably never do that again because there are more strategic ways to do this without being so tedious. If you want to ask questions about that, please do, because that might have been overwhelming and confusing. Now, we've done both the numerator and the denominator. The last step would be to rewrite the problem as it was. The only reason I separated it was to make it a little bit easier to look at. So that would be your final answer at the end. You don't have to do all the steps I did, but it helps to know where things come from. Now, this problem isn't in its simplest form because there's a radical in the denominator. So we're going to talk about something called rationalizing in the next video. So this is a little segue into that if you're curious. 6 is for you to try on your own. There's some extra practice problems. Otherwise, take a look at the radical rules again, write the key points, and come with questions. Have a good night.